Hello everyone, this is going to be another fluids video, and in this video we're going to be continuing our video that we went over the drag coefficient. This video is mostly going to deal with this example problem you see in front. We're just going to go through this and kind of talk about how we do drag coefficient problems. So to start off, I'm just going to read the question out loud. So this is question 41 from chapter 11. So it reads, the oil tanker has a smooth surface area of 4.5 times 10 to the third meters squared in contact with the sea. Determine the friction drag on its hull and the power required to overcome this force if the velocity of the ship is 2 meters per second. Take rho as 1030 kilograms per meter cubed and mu, the viscosity, as 1.14 times 10 to the minus third newtons times second over meters squared. Okay, so I'm just going to go through the process that I do for any kind of fluids problem. So I'll write down what we're trying to find first. So we want the friction drag force. Which we're going to call FD on the hull. And we're also going to want the power required to overcome the force. Okay, and then I also like to write out our givens. So let's change this color. So we're given the surface area. So I'm just going to write this. And that's saying it's 4.5 times 10 to the third meters squared. We're given density. It's 1030 kilogram per meters cubed. We're given the velocity of the ship as 2 meters per second. We're given viscosity 1.14 10 to the minus 3 Newton seconds over meter squared. Okay, so if you recall from our last video, I kind of wrote out the steps we would do to solve this problem. So I'm just going to go over that one more time. So to start off here, first thing we're going to want to do is we're going to want to find the Reynolds number. So recall, so the Reynolds number is rho v L over mu, or rho v D over mu. It depends what kind of flow this is. So in this case, we're going to want to write it in terms of characteristic length, because the flow is external flow across a flat plate, we can say. Okay, so if we actually do that, put in values. So if rho is 1030 kilogram per meter cubed, we can put our velocity. Our length, it doesn't directly tell us the length, but we can see from the picture it's 300 meters. And then our viscosity is given. Okay, so if we evaluate that, we get a Reynolds number of approximately 542.105 times 10 to the 6th. Okay, so our next step now is to determine whether this is laminar or turbulent flow. So if you recall from our last video again, so our transition Reynolds number, meaning the point where it goes from The value we can say where it goes from laminar to turbulent. If this is an external flow, which it is, we say that the transition is 5 times 10 to the 5th. And since this Reynolds number that we're obtaining is greater than that, that means we can say that this is going to be turbulent flow. Okay. So knowing that this is turbulent flow over a plate, we can call the bottom of the ship a plate in this sense. We're going to have to look at our equations for drag coefficient with a turbulent flow over a plate. So let's title this Finding the Drag Coefficient. So you could see in your book, or if you want, you could look at my other video on drag coefficient. But what you're going to see is that to find the drag coefficient for a turbulent flow with an external flat plate, the drag coefficient is the following, or can be obtained from the following expression: 0.455 over log base 10 of the Reynolds number to the 2.58 power. If we evaluate that and plug in our Reynolds number in, we get that our drag coefficient is about 0.00169. Okay. So from here, we would just plug this in to our drag force equation, which we know is just the following. So if we plug values in here, we get that the drag force is equal to 0.00166969. Area projected is the surface area, so 4.5 times 10 to the third. Density is 1030. Velocity is 2. So if we solve that, we get that the drag force is 15.73 kilonewtons. Okay, so that's part 1 to this question. And now we still have to find the power. So recall, power is just going to be, let me write that in a different color actually. So power, we know, is just work over time. So if you think about it, you know that work is expressed as, or can be expressed as, force times the distance. Well, now power, you can also express as a force times velocity. So it's essentially force times distance, but you're going to be dividing that by time to get power, at least. So you know distance over time is just velocity. So that's how you would get that equation. And now to solve that, simply substitute our FD. So 15.73 kilonewtons times our velocity, which is 2 meters per second. So we'd have to convert this 15.73 kilonewtons into newtons. Doing that and multiplying that by 2, we obtain power. So we get a value of power that is 31.4615 kilowatts. Okay. So that is our final answer. I hope you guys enjoyed.